So now, here we have an NPN bipolar junction transistor wired as a switch. Right now the jumper is basically in the off position, right there. We got ground on both sides of the base to emitter. No current is going to flow. We got a 10K resistor that's going to limit current when I put the jumper to the positive supply right there. So a little bit of base to emitter current allows a lot more collector to emitter current. The LED turns on. Now, the reason why I have two series resistors right here, which you could always do if you want, about 1,000 ohms. They add up to 940 ohms together. But when you got resistors in series, they divide up the voltage, which is important for this circuit because I have 14.6 volts applied to the circuit right there. There you can see 14.6 volts. And this would be a 12 volt lithium iron phosphate battery while it is charging. If you use it, you should probably stop at about 12 volts, but you can discharge the battery down to about 10 volts. So we're going to move that right there. This is kind of designed for that change of voltage right there. And there you can see LED is still on. Not as bright as it was, but still not too bad right there. So there we go. We got it on. Transistor is turned on. So whenever you are working with a voltage that you're not really used to. So generally I assume that most people are used to wiring an NPN bipolar junction transistor switch with 5 volts right there. When you get the higher voltage, you have to worry about the power dissipation of the components. And I'm bumping the power supply, that's why the LED turned off really quickly. I could put a capacitor on the supply rail, and that would help power the circuit for brief periods of time where I bump the power supply. And okay, it's not flickering now, but it was earlier. So usually it flickers when I bump it. So in any case, you want to make sure that you don't exceed the power demand. So we could go up to 40 volts when you're just looking at the transistor right there. You could turn a 40 volt circuit on and off. You have to limit current through the transistor. I'm using a 2N3904 to no more than 200 milliamps of current, and I usually try to stay halfway below that. And so the maximum power is 625 milliwatts of power. So these can dissipate a fair amount of heat compared to the resistors. These are a quarter watt resistor, 0.25 watts. This would be 0.625 watts. And so 0.25 watts is the absolute max. You want to stay below 0.125 watts to really make sure they don't overheat. So when we get this higher voltage, 14.6 volts, if I use one 1,000 ohm resistor, it's going to get above 0.125 watts. So not all the way up to 0.25 watts, so it probably won't have a catastrophic failure or it catches fire or something. But still, or gets damaged. Still, better to use two in series. They will divide up the voltage across them. So red LED, as long as you limit the current, you don't have to worry about it overheating. So 20 milliamps of current is the maximum for these indicator LEDs right there. And it's going to be about 13.6 milliamps of current when we, 13.6 milliamps of current. I did the math in a different video. When we have 14.6 volts powering all this and the transistor is on. Remember, this symbol is showing the off position. Go to the positive supply. It's in the on position right there. So it only lets 2 volts build up across it, and then it lets current flow from that point on. And so you're going to maintain about 2 volts across that. So you don't have to worry about wattage. The voltage is pretty much fixed. You just have to worry about the max current. And so, you know, kind of like with the transistor, the max current, because when it turns on completely, it has almost no resistance across it. When it's off completely, then it has the voltage across it, but no current flowing through it. So it's not creating any heat right now. It stopped the current. So either way, they don't tend to get hot too easily. Now the resistors, they're limiting current. They're the ones taking that extra voltage. So 14.6 volts minus the 2 volt drop of the LED when the transistor is on fully, so it has almost no voltage across it. You know, still builds up a little bit, but almost no voltage across it when it's on fully. That's going to leave 12.6 volts across the 2 resistors. So if you just use a single 1,000 ohm resistor, you're going to have that 12.6 volts times about 13.6 milliamps of current. It'll get quite hot. When you got 2 in series, if they were 500 ohm resistors, they would pass the same amount of current. So we just got a little bit more current than a 1000 ohm resistor would let flow through. But we got the two resistors, they're going to divide up the voltage. Out of that 12.6 volts, we're going to have 6.3 volts across that one, 6.3 volts across that one. So each resistor is going to get about half as hot as a single 1000 ohm resistor would get. So they're creating as much heat total as a 1000 ohm resistor if we rounded them to 500 right there. But there's the two of them. So they're both dissipating. They both have, together, they have twice the surface area to let the heat release right there. So now, hopefully that all made sense, but if not, hopefully this multimeter measurements will help illustrate all this. So we're going to set it to V for measuring voltage. Don't have to move the red probe for anything other than high current. Black probe I never have to move. I can leave at COM. But yeah, there you can see all those things we can measure with the probe in this spot. So I still have the power supply set to 10 volts. So now, if you're using a 12 volt lithium iron phosphate battery, 10 volts is the absolute minimum you let it discharge to. You're probably better off just recharging it once you get to 12 volts. But black probe, we're going to go there. And then red probe, I think this will work better if I just use the alligator clips for the jumpers to get our measurement point. So first we're going to look at how much is actually making the rail. Right now the LED is off, so no current is flowing right there. So basically 10 volts right there. We got a little resistance where the connections are and stuff, but it's going to be pretty much the supply voltage right there. And as current flows, the voltage will actually dip down a little bit. So now we have the red LED, so it is going to drop some voltage right there, even though current's not really flowing. So it's kind of unpredictable what you're actually going to get. But we go up to where the resistors are, and there you can see about 10 volts right there. Now I am going to come back to the transistor, and we're going to turn it on. So that's up at the collector. We're going to turn it on. Again, we're at the 10 volts, and there you can see there's almost no voltage because it's connecting to ground pretty well, even though the LED is lit up. We'll have about 2 volts if I go to the anode of the LED, where the LED and the resistor connect together right there. We got about 2 volts. And then across both of the resistors. So we're just looking at the resistor voltage. I got to bring that jumper up there. We got the rest of the voltage, about 8 volts out of 12, and I think there's a little bit of a loose connection. That's why it's kind of drifting right there. So that's at the lower voltage range, and across each one of the resistors, I'll come up to where the two connect together right there. We got half of that 8 volts. We're going to have about 4. That's the bad spot on the board I was trying to plug into. 4 across that resistor, and then there'll be 4 across the other one. If I move this over right there, that's while they're on. Each one of them has about 4 volts. Once I get into the right spot, I forgot about the bad hole, and there we go, about 4 volts across it. So hopefully that makes sense. Now, when it comes to those two resistors, 10 volts, we could use a 470 ohm resistor by itself. You definitely can with 9 volts. That's usually what I do. But I designed this circuit so that we can get up to about 14.6 volts. That's when a charger is applied to a 12 volt lithium iron phosphate battery. That's what it charges it to. And then when you remove the charger, it rests down at 13.6 volts. It drops down quickly, but the higher voltage pushes more charge into there. And there you can see the voltage across one of the resistors right now. So it's half of the voltage that's going to be across the 2 of them. So we saw that we will get the same voltage across the top one there. We looked at the bottom one. You know, basically it might be a little bit different. And then we'll go back to ground right there and to the negative supply. And we'll see, since the transistor's on, we got almost no voltage across it right there. It's as close to a perfect conductor as it can be. It's not perfect. So something I'll always be aware of when you're working with transistors. And transistor is off now. I can also go to the negative supply. I don't have to go to the negative supply to turn it off. Once you cut current from base to emitter, then it turns off. So there we go. We got about 13.2 down there, but that's because not all the voltage is making it through the LED. I go up to the resistor, and there we got it. So we can see when I turn it on now, the LED because the transistor added just a little bit to this, but the LED is basically building up about 2 volts across it while it is on. And then that's out of the 14.6 at the supply, and so on. So in any case, we got this range of voltage. That's the main thing. So when you're designing a circuit for a range of voltage, the most important thing is that actually we can open the circuit, and so I'm not going to reattach the alligator clips. I don't have to. We're going to measure current. So again, we're at that 14.6 volts. We can see how much current is flowing through here. And if I remember right, it was 13.6 volts according, or 13.6 milliamps according to the math that I did earlier. So set to milliamp setting, I can measure up to 600 milliamps, I am pretty sure, with this meter. You have to put the current through the meter. So all series components, it's wired to be on, but we have a gap. So the LED is not on, but there is a little bit of base to emitter current flowing. Not much though, because it's a 10,000 ohm resistor. And I complete the circuit through the meter, and there you can see just shy of 13.6 milliamps of current. So that's the same as 0.01345 amps. You do the math in amps when you do Ohm's law. But in any case, that's what we got right there. So all of these circuits that I show, usually I don't do the measurements right there. I'll say the math or whatever, and so on. When you're learning about the math, actually build the circuits and take multimeter measurements. Now, definitely get the meter off of measuring milliamps as soon as you're done measuring, because right now this is set up so we could measure voltages somewhere. If I see this is on, I might think it says voltage. It actually does right now. But if it's at the milliamp setting, if I see it on, I might think it's ready to measure voltages. But if you measure a voltage that doesn't limit the current, then you will blow the fuse if it's a higher current than what the meter is set, and maybe damage the meter, but I think the fuses do a good job protecting the meter. So you blow a fuse, you actually have to open it up and replace it. I'm pretty sure I have to replace the 10 amp fuse in here now. But yeah, that's really about it. I wrote the range of voltages for the battery, and 12.8 volts is the nominal voltage. If you get a 12 volt battery, that's what it's going to say. But half the time it's higher than that, half the time it's lower than that when you go from fully charged to fully discharged. So fully charged is 13.6 volts, but the charger will push in extra current at a higher voltage in order to pack more charge into it. And so just be aware of that. If you have a circuit that's wired to a battery that can be wired to a charger, you will get up to 14.6 volts at that circuit. And so 12 volts is probably a good spot to stop using it, but you can squeeze out a little bit more of the stored power. Go down to 10 volts, but below 10 volts, you start damaging the cells. The individual cells can be discharged to 2.5 volts. There's 4 of them in a 12 volt lithium iron phosphate battery right there. And so when each one gets to, if any of them get to 2.5 volts, drops below that, you have the potential of causing damage. They may not always be balanced either. So another good reason to stop at 12 volts. One of them might be a little bit lower voltage than the other ones. When you fully charge it, that should help balance it. So fully charge it often. And they should stay balanced, but they don't always do. Hopefully there's protection circuitry there in them to protect them though. And also with the transistor, when you look at the symbol there, the arrow is the emitter, the side over here is the base, and the side without the arrow is the collector. It may not be circled. Now, there should be a part number next to it if it's on a schematic diagram, but not always. I think there usually is a part number on there. And you can look that up for the pin layout. So I already drew the pin layout right there. That's for the 2N3904. Not all transistors, but if it starts with 2N, and whether it's NPN or PNP, this is the pin layout that I've been seeing. So that's only if it's bipolar junction transistor. There's other components that start with 2N that are not bipolar junction transistors. So to wrap this up, with these higher voltages, about 1,000 ohms is perfectly fine for protecting the red LED. You can see it's plenty bright. That's at 14.6 volts. I'll drop it down to 10.6 volts. I'm guessing it got dimmer. I wasn't looking at the screen. But in any case, that's plenty bright right there. 1,000 ohm resistor will work fine, but it'll get quite hot. Probably won't exceed the 0.25 watt maximum of these quarter watt resistors, but still, it'll get quite hot. So if I put two resistors in series that are half of that total resistance right there, each one of them will only have half the voltage across them, about the same amount of current flowing through them, and therefore each one of them will get about half as hot as that lone one will. So definitely safe here. So hopefully that makes sense. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.